Hi, my name is Adrian Sampson. I'm going to be talking today about our Micro 2013 paper called Approximate Storage in Solid-State Memories. And this is all about exploiting the properties of future memory technologies, including PCM, to make them more efficient, to make them higher capacity and faster when they store approximate data. And we're going to take advantage of two properties of PCM, namely the underlying analog substrate that's present in PCM and other memory technologies, and also using unusable space, that is parts of memory that can no longer be used otherwise because they contain failures. We're going to put to work storing approximate data. And this is work I did here at UW and during an internship at Microsoft Research. And my collaborators were Jacob Nilsson, the grad student here, Karin Strauss, who's over at MSR, and Luis Ceze, one of my advisors. First, let's talk a little bit about approximate computing. Approximate computing is becoming a little bit of a hot topic in the architecture community. And there's been lots of great research over the last couple of years on how to do approximation in the CPU and in accelerators and in software. In fact, there were two other papers at Micro this year that talked about doing approximate computing either in specialized processors, in this case a kind of vector processor, and on GPUs. And all this research is really promising in its ability to trade off the error properties of these computational systems in order to make them more efficient for systems that can tolerate it. All this approximate computing research is really exciting in the way that it allows these computational systems to trade off their accuracy for efficiency of some metric. But this is all part of a larger picture in terms of the computer system. All these systems have to do with computation, and there's many other things that are involved in getting work done in computer systems. There are many other components that can exhibit the same trade-off between efficiency by some metric and accuracy. In this talk, I want to try to broaden the conversation about approximation from just computation to talk about storage. In particular, what I mean is persistent disk-like storage that we use hard disks and flash for today, and main memory. That is what you usually think of as the role that DRAM plays today. And I'm interested in how we can trade off accuracy for efficiency in these systems. To motivate why I think this is important, I want to show you this screenshot from my advisor's phone. You can see that a lot of the storage on his phone, and a lot of the storage on my phone too, is taken up by photos and video and audio, exactly the types of data that don't need exactly precise storage. And it's not just mobile devices, and it's not just persistent storage. You can also imagine very large systems, like, for example, a huge machine learning system on a cluster. A deep learning system, for example, needs lots and lots of access to very high performance data, high performance storage, but its overall usefulness won't be compromised if a few mistakes are made in storage of that data. This is also true of other settings, like, for example, a mobile app that does augmented reality. It needs lots of storage, it needs to be really fast, but small errors are unlikely to perturb the execution perturb the usefulness of the app. There's also a sensor logging, where we're recording inherently approximate data, and we need to store a lot of it, but each individual data component isn't particularly important. When I talk more about approximate storage, I want to keep in mind two themes that we've learned from doing approximate computing research in the past. The first is interleaving. The fact that all programs are not completely approximate. The programs have certain data, certain parts of their computation needs to remain perfectly precise. So it doesn't suffice to design a storage system that always has errors in its data. We need to be able to configure whether the storage is in a precise mode or an approximate mode for any given chunk of that data. The second theme is error mitigation, and that is to say that total garbage is not a good approximation. That is, even when data is approximate, even when we can tolerate some error in it, we want to exploit the underlying hardware in order to do our best to mitigate the magnitude of the errors in stored values. These things are going to come up in the two techniques that I'm going to describe for doing approximate storage in PCM. Let's talk a little bit now about PCM, phase change memory, and why we're excited as an architectural community about using PCM in future memory systems. And it offers, one of the reasons that we're so excited about it is that it offers some of the advantages of flash, existing mass storage systems like flash memory, and of main memory systems like DRAM that's pervasive today. First of all, we're excited because it is likely to surpass the scaling limits that are upcoming for DRAM. It's likely that in the next few years, DRAM will stop scaling as well as it has in the past, and we'll need a new technology like PCM to scale further. It's also almost as fast as DRAM for some definition of almost, and we'll get to that later. What it brings from the flash side of things is that it's non-volatile. It has this interesting property that it doesn't need power to maintain data, unlike DRAM. It's also likely to be much faster than flash. So these are properties that make us excited about PCM, but PCM comes with its own quirks that will need to be solved if we're going to use it for main memory and persistent storage. One of the quirks is that almost from the previous slide, is that PCM is not quite as fast and it's not quite as low power as DRAM. And so in order to make it viable, to make it a good competitor to DRAM, we're going to need architectural techniques that make it fast to access, make it fast to read and write, and make those accesses as low power as possible. The other quirk that DRAM doesn't have is that cells wear out over time. That is, during the normal lifetime, during the expected lifetime of a PCM device, blocks will have failures. This isn't just something that happens near the end of a lifetime, so we're going to need techniques that mitigate the effect of errors, failed cells, in PCM arrays in order to make them useful throughout a normal lifetime. And any technique that can extend the useful lifetime of PCM will be beneficial. So these are the two quirks that our community is focusing on when making something like PCM relevant for doing main memory storage and persistent storage in future devices. That PCM is not quite fast enough, especially in the high-density multi-level cell configurations, and that cells wear out over time, and those cells can't be used for precise storage. But because I'm an approximate computing person, when I look at these constraints, I don't see hard constraints. It's possible to think of these as trade-offs with accuracy. In particular, PCM can be slow to access if you need the storage to be completely precise all of the time. Secondly, parts of the memory can no longer be used when they experience failures if you can't tolerate a few bit errors in the data that you store. But by using approximate data, by running applications that don't need exactly correct storage all of the time, we can relax both of these constraints and hopefully make PCM a near-term replacement for DRAM and flash. One way of looking at this trade-off is to think of traditional memory systems as having a strict trade-off between their speed and their density. And what we want to do is introduce a third dimension that trades off also their accuracy by saying that PCM is allowed to be less accurate when storing approximate data. We can make it faster, higher capacity, and longer lasting, or both. So those are the two techniques that I'm going to be exploring in this talk. First, we're going to trade off accuracy for performance in the accesses of the multi-level cell devices. And I'm going to look at using worn-out memory, that is memory that would no longer be useful for doing precise storage to store approximate data in this sort of dark matter of PCM as it wears out. And that's also the outline for this talk. I'm going to talk about one of these techniques first, and then move on to the error tolerance technique. So first, let's talk about multi-level cells. And as background, what exactly is a multi-level cell? A single-level cell, it's a little bit of a misnomer, but has two different levels of some analog value inside each individual storage element in a PCM memory. What I mean by that is that PCM and other memory technologies are quantizing an analog substrate to expose digital storage, a 0 or a 1 stored in every cell. And there's some underlying analog value that's either high or low, indicating a 0 or a 1. In PCM's case, that's the resistance, and that's proportional to the crystallization of the chalcogonide material that's inside each cell. And what this means is that when the resistance is high, that's a 1, and when it's low, it's a 0. So there's two levels in this cell, and we call that, for some reason, a single-level cell. Multi-level cells, as you might have already guessed, use multiple analog values to represent more than one bit. So we're packing more than just one bit, more than just two values, into a single cell. Here I'm showing a 4-level cell that can store 2 bits. The way you write to a multi-level cell is to try to get the analog value stored in the cell as close as possible to the analog value that corresponds to the desired digital value that you want to store. And of course, because this is an analog system underlying this digital storage technology, the write is not perfectly precise. What I'm showing here is a sort of a cartoon of the probability distribution that happens when you use an analog write to get as close as possible to the desired analog level for storing a 1, 0 in this 4-level cell. And because the analog write systems are imperfect, you can think of this as a probability distribution that's centered on the desired value, but is spread out some. And the goal of a precise storage system is to get this probability distribution very narrow, so it's practically impossible for when you're writing one of these analog for one of these digital levels for that to be confused with a different digital level when it's read. As you might have already guessed, that the core idea is behind approximate storage using multi-level cells is just to widen this distribution under the hypothesis that I'll verify later that writes to multi-level cells are slow when they require very narrow probability distributions. But if you're allowed to be sloppier, if you're allowed to use a wider probability distribution with your analog writes, then those writes can be faster and use less energy. This way, by widening the probability distribution, by loosening the requirements on the analog writes to multi-level cells, we can make them faster and thereby, as a proxy, allow more levels in a single cell given a performance budget. So again, let me bring up this triangle. You can think of the number of levels in a cell as representing a trade-off between the performance of a typical PCM system with the density. The more levels you pack into a cell, the more accurate your writes have to be, and therefore the slower those writes are. If you allow the probability distribution to be wider, if you allow sloppier writes, then you can have errors, but that means that you can either make your cells faster or you can pack more levels in a cell given a performance budget, or both. So how exactly does this work in real PCM systems? So the way that the writes work in typical multi-level PCM cells is using an iterative approach. That is, each individual write pulse that you can send to a PCM cell is not accurate enough to set a desired level to a desirable accuracy in a PCM cell. So systems use an iterative approach. They'll send a write pulse, read the value back, and if it's not close enough to the desired target value, then you'll write again, either increasing or decreasing the resistance each time. And so what I'm showing here is a resistance that starts low and is increased by a couple of pulses, overshoots its target, and needs to be brought back in order to reach the target range that will prevent the sources of analog error in the cell from confusing the stored value with one of the neighboring digital values. The key idea with approximate storage in this system is just to widen the target range, is to take that threshold for terminating the write process and to make it looser. So that in this example, the target range is hit one iteration earlier. And by using fewer iterations, the writes go faster and they use less energy because each write pulse consumes energy to melt and recrystallize the chalcogonide inside of the PCM cell. Now we'd like to move on from the mechanism to one of the ways that we can reduce error in stored values in approximate MLC configurations. And this goes back to the theme I asked you to remember before about how to mitigate error, mitigate the magnitude of errors in stored approximate data. And one of the interesting things about approximate MLCs is that they exhibit really good error characteristics if you want to store values that are the same width as your cell. So on this slide, I'm showing a 4-bit cell and if you're storing 4-bit words in these 4-bit cells, if for some reason you really like 4-bit words, then this has exactly the error characteristics that you want. That is, the low bits have relatively likely error because nearby levels are likely to be confused for each other in the approximate MLC, and high bits have relatively infrequent errors. That is, it's less likely for errors to have larger magnitudes of errors in this value. But in reality, we don't just store 4-bit numbers in memory. Unless you have some very strange application that really likes 4-bit numbers. Realistically, you have wider numbers. And here I'm showing 4-bit cells storing a 16-bit number. And in this case, it's not as clear that the approximate MLC has the errors that you want. In fact, because the 4th highest order bit in this word is stored in the lowest order bit in one of the component cells, there's a relatively likely to be an error in that bit, which means, and in this case, that's a very large magnitude error for the 16-bit number, and that's bad. By concatenating all the bits from these 4-bit cells to make up the 16-bit number, we have pretty bad error characteristics, relatively large probability of large magnitude errors. To do this a little bit differently, we can encode the values in a way that mitigates the amount of error in each cell. Here I'm showing a sort of striping encoding, where you take this 4-bit cells and you map the highest order bits to the highest order bits of each of the component cells, and the lowest order bits to the lowest order bits of the cells. What this means is that that same bit that was causing us trouble before, that was causing large magnitude errors, is now much lower order in the stored word. By doing this interleaving coding, we in practice reduce the amount of error in stored values by quite a bit, and this leads to higher quality output for the approximate programs we measured. It's not perfect, and I think there's a lot more interesting research to be done on how to encode values for approximate storage and approximate transmission, but this works really well in practice. Now I want to show you some results of using approximate MLCs to store data for applications. And in this evaluation, we actually use 2 different types of data sets to evaluate the technique. And that's what you're seeing along the x-axis here, is that one set of applications are main memory benchmarks. And by that, I mean traditional applications that we've used in previous work on doing approximate computing on the computational side. That means that a portion of their memory is marked as approximate, and some of the memory, like the pointers and things, are marked as precise, and then stored in main memory. And I also evaluated a second set of benchmarks, and these are not programs, but just data sets, just blobs of approximate data that are meant to be stored persistently. And that's a set of images, for example, or I looked at a neural network and I stored the network parameters, the neuron weights in approximate memory, and then read that neural network back and measured the accuracy of the classifier after storing the data in approximate memory for some time. And on the y-axis, what you're seeing is the best write speedup when the application output error was limited to 10%. That is, we explored lots of different speeds of writing, lots of different threshold values that led to different numbers of average write cycles for this approximate MLC, and we chose the one that for each application led to less than 10% output error. And so what you see in these applications is that on average writes are 1.7x faster for approximate data than for precise data when quality loss is limited. You can also see that the main memory benchmarks are slightly less error tolerant than the persistent storage benchmarks. Now we'd like to move on from the approximate MLC technique to the second approximation technique for PCM that we examined, and that's using worn-out memory that could otherwise no longer be used for precise storage, and putting it to work for approximate storage. So the thing to understand about PCM for this technique is that failed cells are a fact of life. Eventually, you have this perfectly good block, and along come hard failures. Some of these bits will get stuck, and you can no longer flip them from a 1 to a 0 or a 0 to a 1. And the reason I have tragically on this slide is that there are all of these bits that are perfectly good, and there's just a few of them that are failed. I wish that we could store data in this block using all those useful bits while ignoring the failures. And the way that this is typically dealt with in PCM systems and other systems that are prone to hard failures during the useful lifetime of the array is to use correction bits. That is, to add on a few bits to each fixed size block in the array and use those bits to correct the failures, to indicate the stuck bits in the data block. This works great. Lots of research has gone on to find ways to most efficiently correct bits in failed blocks in PCM and other memory technologies. This works great until another failure occurs. The important point is that error correction resources are finite. Eventually, each block will exhaust the resources it has to correct all the failures that can occur. And on this slide, the block is provisioned to correct 2 failures in the block. And when the 3rd failure occurs, then this block becomes bad again. And it's no longer possible to store data. And this is, again, tragic. To look at this block, there's plenty of bits here that are perfectly good, and it would be great if we could store data in this block and just tolerate the error, tolerate the uncorrectable failure in the data block. And of course, that's exactly what we're going to do. As an approximate computing person, when I look at this bad block, I don't see a bad block, I just see an approximate block. This is a great place to put data that can tolerate a few bit flips. And that's exactly what we do. take data in the program that can be approximate and map it to the otherwise unusable blocks, those blocks with uncorrectable failures, those that have exhausted their error correction resources, and put that memory to use. And there's one more thing that we can do to make this technique even more viable, and this goes back again to the theme of mitigating errors in approximate storage. And that is that we don't have to naively correct only those errors that crop up first. That is, that all errors are not created equal. In fact, because our correction bits can be used, our correction resources can be used to correct any failure in the cell, we don't need to correct those errors randomly. We can correct the errors that are likely to do the most harm. In particular, we can steer those correction resources toward those bits that are higher order in their words, and prioritize those bits over the lower order bits in the word. So if we have to correct, in this example, 2 of the 3 failures, we won't just correct the 2 failures that occurred first. We'll reallocate the correction resources to correct those bits that will do the most harm if they have failed. So this allows us, again, to significantly reduce the magnitude of error in stored approximate values just by redirecting the error correction resources we already have in the cell to those bits that are the most important. Now I want to again show you some results for using this technique, and on the x-axis you see the same benchmarks, the same main memory and persistent storage benchmarks, and this time on the y-axis you see the normalized lifetime of the cell that is measured in writes. How many writes can you do to the entire array before it has to be replaced, before it exceeds some margin of failed blocks? And what we see is that across all the applications, the lifetime is extended by 23%, or given some assumptions about the write rates, that's from about 5.2 to 6.5 years. So we extend the lifetime of an array by a little more than a year. And again, we see that the persistent data benchmarks are a bit more error tolerant on average than the main memory benchmarks. So those are the 2 techniques that we've explored for doing approximate storage in phase change memory and in other memory systems. And the reason I'm so excited about this work is it helps broaden the conversation about approximate computing just from the compute side of the equation to a more broad look at components of computer systems that can benefit from this type of trade-off. And what I want to leave you with is the notion that I think that as an architecture community, we could do well to focus our efforts on approximate computing more broadly than just on the computational sides of things, on parts of the system that architects don't typically think about. In particular, there's this gray part of this diagram I've been showing you, which is the I/O. I don't exactly know what it means to approximate the display or the network, but these components take up most of the energy spent in mobile phones, the radio and the display. And if we can do something that trades off the user experience, and it trades off quality in slight amounts, but saves a lot of energy in these areas, that might be even more effective than approximating computation. Thanks so much for your attention.